Okay, I want to explain about the star clusters. Let me share my screen. Yeah. Calculation of isochrones. The calculation of theoretical isochron is lines of equal age is done with stellar atmospheres. 3 parameters as metallicity X, Y, Z, 0 age main sequence, T effective, and L, which is luminosity, chemical and gravitational evolution, T effective and luminosity, adequate stellar atmospheres, physics, absolute fluxes unfolding with filter curves, and colors, absolute magnitudes, and so on. Which astrophysical parameters are important? Equations of state, opacities, model of convection, rotation, mass loss, magnetic field, and core overshooting and abundance of helium. Here you see different isochrones. Here different treatment of convection. You see different isochrones for different treatment of convection. Which it shows that convection is has some influence in isochrone, fitting the isochrone. A comparison of isochrone sets. We have different kind of isochrone sets compared to following isochrones: Padua, Parafe, Geneva, Y square, Y et al, and Cs. Here you see the location of the sun with isochrones of 5 gigayears. Isochrones by Cs et al. 1997 seem to have a problem, as you see here. And if the isochrone does not fit the sun in its line, it has some problem, as you see here. And here it is the comparison of different masses for a constant MMV, visual magnitude, and zero line is the isochrone of the Padova group. And you see here visual magnitude and delta mass, and here you see 4 different sets of isochrone groups, and you see the isochrones are different. Also here you see the comparison of different color indices for a constant visual magnitude. Zero line is the isochrone of the Padova group. You see visual magnitude, and here models for different colors. And the isochrones are different, as you see. Also here you see for 6 famous star clusters, which we know already. You see the age, reddening, and metallicity. And if we fix 3 of them, for example, if we fix the age, metallicity, and reddening, but the distance modulus is different, and then we see the output is different, as you see here. But we can say it is the transformation in distances, which is in parsec. And for Barafe, you see the numbers are so similar to here. And the mean value is minus 13% plus 7% for Barafe and Y et al. For 1 free parameter, which is distance modulus. And you see the number of them. And you see here the numbers are somehow different. Some of them is decreasing, some of them increasing. Here it is in a statistical point of view, it is significant for a given reddening metallicity and age. The isochrones by Baraf et al. Yield significantly brighter and yet significantly fainter absolute magnitudes. In addition, the isochrones by Cis et al. Do not reproduce the location of the sun correctly. You see here different kind of isochrones for different kind of isochrones for which they are for different groups. For NGC 1817, as you see, for each group, and the isochrone is different. Here, age determination only based on these 3 stars. For example, we have isochrone and main sequence. If these 3 stars are from belong to this cluster, so the isochrone should fit them. If not, isochrone won't fit for these 3 stars. And you see here the isochrone for Z or other metals is 0.040, and look at T, age is 8, 8.1 and 8.2. You see the result that T is 130 million years, reddening E B minus V is 0.75 magnitude, and V minus MV is 14 magnitude. Also, you see here the allogaty is 7. Here isochrone main sequence. Here you see 2 of them fixed, 1 no. But here you see also 2 of them fixed, 1 no. Also, we have automatic methods. Definition of different important areas or boxes in the CMD or color magnitude diagram. Do this allocation as you like. You can circle the elliptic, and you see different elliptics, and then for each star we have 1 box or 1 circle, 1 elliptic, and then we count the stars which are in this circle. For example, if there is a star, if there is a circle here, and we have 10 stars here and 5 stars here, but in here, for example, we have 10 stars and then we have 1 star here, we fit for this isochrone in here. But for example, if we have also 10 stars here, 8 stars, 6, 5, 2, but here we have 10, 1, 1, 1, 0, we draw the isochrone for this line. So we draw the isochrone for the group of the boxes that in one length, in one direction, that they have more stars in their boxes. And just be careful that you always lose the stars because of discrete boxes. Only for T is more than 300 million years, it is. Other methods, and you see, for metallicity as X, Y, Z, or hydrogen, helium, and Z is the rest of them. But the sum of all of them should be 100 for sun. In the literature, you will find Z or Fe over H, hydrogen, M over hydrogen, or element 1 over element 2. Relation for the transformation are necessary, as you see here. Also here, transformation of iron over hydrogen to Z or the rest using y is equal to 0.23 plus 2.25 z from Girardi et al. Applied in this work. And here you can change the logarithmic to linear. This is related to logarithmic. And we can say the sun is, we can consider it as a standard star. Our standard star for the normalization of the metallicity is the sun. We define mass, luminosity, absolute bolometric magnitude, temperature, spectron type, color, age, chemical composition, internal structure, rotation, magnetic field, convection, diffusion, pulsation. And we can say in abundance analysis, you see we have ingredients, stellar atmosphere, atomic line data, high resolution spectral analysis method, starting parameters. And for starting parameters of the sun is T effective and luminosity. And you see the other stellar atmospheres here. Different synthetic for stellar spectra for the same star. You see here we have wavelength and F, and you see we have different synthesized spectra, stellar spectra for the same star, and therefore different groups, as you see here, but they are different. Also you see the lines have some different with each other. And in here we can say, what can we do to have a spectra of the sun? We should point our telescope to the moon. We cannot have the spectra from the sun directly, but we should point our telescope to the moon, which is the second brighter object in the sky, and take a spectrum from the moon. Then we have the complete spectrograph from the sun. Because the moon itself does not emit any flux. We just see the moon because it has the reflection of the sunlight. If we don't have moon, we can use asteroid. But be careful, do not use comets, because comets have gas and dust. We have some problem with abundance in the sun. For example, for hydrogen, helium, elements with only a few lines, elements with only weak lines, and LT versus non-LT. LT means local thermodynamic equilibrium, and NLT means non-local thermodynamic equilibrium. Problems with abundance of hydrogen in the sun are the shape and depth of the Balmer line is not depending on how much hydrogen is in the sun. The atomic level of hydrogen in the sun is saturated. The shape and depth of hydrogen line do not change with the absolute abundance of hydrogen. So with Balmer and Paschen lines, we cannot determine the amount of hydrogen. And for the helium, we can say there is no helium line in the solar spectrum. The more and strong lines we have, the better we can estimate the abundance of the lines. And you see the abundance in the sun, also for meteorites. Also, we can use meteorites too, or asteroid. And you see here the abundance in the sun And we can, as you see, maybe someone thought that Fe or iron is the most element in the sun, but no, it's not. We have first it is hydrogen, then helium, oxygen, carbon, nitrogen, and then NeMg, silicon, and then we have iron in the sun. But iron, or Fe56, is the most stable element in the universe because it has the highest binding energy. So it is very difficult to destroy iron in the nature. So it is forever. If we look at the spectrum of stars, we always find iron lines because iron is stable. These are two reasons why we use iron abundance in metallicity. And we can also say, how can we know that how much hydrogen and helium is in the sun? We can have hydrogen and helium estimate from the comet and asteroid. As you see, no, you don't see it. And we can have hydrogen and helium estimate from the comet and asteroid because they were born at the same age of sun. In sun, we have ionized hydrogen and helium, but in comets and asteroids, we have hydrogen and helium with other elements. And it is important that you know that carbon and oxygen are the most elements in the universe, and we ourselves are carbon species. Most of us, our elements are carbon. Here you see that if the element abundance value in the sun changes, the value in star clusters will be changed. The abundance on the sun depends on different methods and different stellar atmosphere. It is not stable. As you see here, because we measured other star clusters value of them for elements, and because the base of them is sun, we have sun, and we measure, for example, for the, as you know, for the base star, or it is our sample, we call it 0 or 1, and then we measure the value of other elements in other star clusters with sun. So if the abundance, or if the value of the elements in the sun changes, we should change the other values in other star clusters. And you see here the present day photosphere for hydrogen, helium, and other elements, and also for protosolar. And you see that they changes during the time. Also, they are different for different groups, as you see. Determination of the metallicity. The determination of the metallicity can be done in 3 ways: spectroscopic abundance analysis, fitting of isochrones, photometric calibration, and also ISO-Gaia survey. And you can find it in Gaia iso.eu. Here you see different abundance of elements of different spectra. For example, we can say if we have, for example, O spectra for the star, we have, for example, silicon 2, Mg2, hydrogen. Hydrogen is high. In B2 type star, we have silicon, helium 1, and a little Mg2. For example, in K0 type star, we have calcium 2, we have iron little, iron 2, iron 1, and the other elements, as you see here. It is the spectral type of stars for each type of stars, O, B, A, F, G, K, M, N. And for here is the elements of the how much or how many elements we have, the amount of the elements in different types of spectral type. You see here the isochron for 10 million years. Metallicity can change the isochron. We can say more metals mean more opacity. Opacity means more flux is kept inside the star cluster. Metallicity changes the flux in the stars. Metallicity has very influence on T effective and luminosity, and it can change them, as you see here. Also, it is color diagram. For hot stars, practically no dependence on Fe over hydrogen or iron over hydrogen. If we do not consider reddening, we have this type of isochron that it is not like this, that has some difference and some discrepancy. But here, it has no discrepancy. Thank you for your attention and see you next time. Bye.